Okay, hello and welcome back. We're moving on to chapter 4. It's called second order linear PDEs. I just want to preface before we get too into things, what is the second order linear PDE? In first order, I wasn't really restricting myself to being linear. We were able to tackle some nonlinear PDEs in first order, but in second order, we can really only tackle the linear PDEs before, the problems get out of hand. So what does a generic second order linear PDE look like? Well, let's jump back to ODEs. Second order linear ODE, you should remember this from your ODEs course, took the form, it had some coefficients on each of the orders, right? So let's give myself two orders there, first order, zeroth order, maybe a function on the right-hand side. And we had coefficients, which I would normally call m2 of t, m1 of t, and m0 of t, and then these all got added together. And then maybe you had a initial condition, y at 0 was y0, and maybe an initial velocity, y1. So that'd be like the second order linear ODE, where basically we want to think, okay, we've got some multiplicative functions, and then maybe a forcing function. I guess that should be f of t, not f of x, but if I'm working in a variable t. So you have multiplicative functions and forcing functions, and so we're going to do the same sort of thing with PDEs, where the generic second order PDE is going to have, let's say I'm in 2 dimensions. So if I'm in 2D, we're going to have something like partial x squared phi plus some space partial x partial y phi plus some space partial y squared phi some space partial x phi partial y phi and maybe a forcing function of x and y. And then I have some multiplicative terms here, so we can think about maybe m xx of x and y, m xy of x and y. The subscript I'm just saying agrees with the how many derivatives I've taken of phi, m y x of y, maybe m x of x and y, maybe m y of x and y, and then maybe just m of x and y. So a whole bunch of multiplicative terms on a whole bunch of phis, right? So even in 2 dimensions, we already have up to, how many terms is that? Seven total terms in the second order linear PDEs. But that's going to be the generic case of second order linear PDEs in 2 dimensions. And then of course, if we increase the dimension farther, then it gets even more and more complicated. So we will see eventually that one way of constructing these in generic dimension is as the following, where we put a matrix valued function in between two gradients. We put a vector valued function in front of one gradient. We put a scalar valued function in front of 0 gradients, and then we have some forcing term on the right. So that's another way of thinking about kind of the generic second order linear PDE in arbitrary dimension. So either of those, but once again, all you want to think is the only actions we're performing on our scalar field that we're solving as a solution, phi, the only actions are multiplying by another function, taking derivatives of other functions, and then adding things together. So we're never performing a different function of phi. So like log of phi is not allowed, phi squared is not allowed, and similar actions like that. So only multiplying by other functions and adding them together. And what we have kind of in the most special of these cases is the 3 fundamental second order linear PDEs. These are also known as the Holy Trinity sometimes. You'll hear it referred to. And this consists of the Laplace's equation, heat equation, wave equation, which I did actually cover in section 1.1 of the book. So the very first video you watched. We covered these as well, but I'll go ahead and cover them again here with a little bit more derivation, so we kind of get an understanding of what's going on with these very fundamental second order linear PDEs. So we'll start with Laplace's equation. Way back in section 1.1, I talked about soap films extending between the edges drawn by a wire. And we can definitely think about Laplace's equation as an approximation to that, but in fact it did have to be an approximation. And there's a much more mathematically pure reason why we would care about Laplace's equation. This corresponds to like complex analysis sometimes. Where you ask questions about analytic functions in the complex plane. We can't really get into why that is, but this is intimately related to that. But really everything that the Laplace's equation, which we can think of as either in 2 dimensions, just the sum of second derivatives in both of the dimensions, or an arbitrary dimension, the sum of second derivatives in every dimension, using that Laplace operator. The reason why we care mathematically about this equation is that solutions of this equation are going to satisfy something called the mean value property. So I'm going to describe the mean value property here, and we'll get an intuition for what this property is before we start solving Laplace's equation and getting functions with this particular property. So the mean value property is a property of scalar fields, for which if I integrate the scalar field over a ball with a specific radius, and then I average over the size of that ball, so that's the mean part of mean value, I'm going to average over the size of the ball. If I integrate over the entire ball, I actually recover the value in the center. So integrating a scalar field over a ball and dividing by its volume gives the value of the scalar field at the center. Okay, and I think what's special here, because there's the mean value theorem, which says that the mean value theorem would say that this value needs to be achieved somewhere within the ball, but the mean value property is specifically when it occurs at the center. So we care about when this is equal to the value of the scalar field at the center of the ball. Let's be a little bit clearer about what this notation is, because that's maybe a notation you haven't seen before. So the notation, capital B of a point, there's always going to be a point first, and then secondly a radius. This is always how it's notated if you get into graduate, postgraduate math. This is a very common way to notate balls. So if you're going into grad school physics, grad school engineering, etc., you'll see this notation for balls all the time. So there's a point in the first entry, and then there's a radius in the second entry. This is the d-dimensional ball centered at the point, or in this case, the point x0, so that's the center, with radius r, or in my other case, radius r here. So radius, and then the center is x0. We can write this down kind of in our domain notation, right, or the notation with omega that you've all been getting very used to. The ball centered at x0 of radius r is simply all of the points in d-dimensional space, where if you look at the distance, this is the distance from the center. Okay, well, if the distance from the center is strictly less than r, that's the definition of a ball. Okay, and there's a very special difference between the definition of a ball and a sphere. Let's make a comment here that the ball, you'll notice, is everything inside of a specific radius, so it's solid, and not including the radius. That's a definition for a mathematical ball. The mathematical sphere is going to be the boundary. So if you've gotten very used to boundaries of domains, you can think about the sphere as the boundary of a ball. Anyway, the definition of this mean value property is just, hey, if I integrate over balls, phi over a ball, and divide by the volume, I get the value of phi at the center. Don't worry too much about kind of this definition for the total volume of a d-dimensional ball. It's not terribly important. You can think about when d is 3, this should be 4/3 pi cubed, pi r cubed, and then in 2 dimensions it's pi r squared, and so on. So that's how you can think about it. But in very high dimensions, just don't worry about it. It's not going to show up, and if it does, you can totally look up what all those numbers mean. So that's the mean value property for balls. I was talking about how spheres are very closely related. I'll just mention this at the bottom again. Balls are solid / domains. Okay, so they're open sets and they fill space. They have a positive volume. Spheres are their boundaries. In other words, are shells. Okay, so a sphere is going to be hollow. It's going to be the shell of a ball, and the ball is going to be solid and be a domain, be open. So we do have this nice proposition that just says, hey, if you have the mean value property for balls, which is the one that I stated originally, you actually have the mean value property for spheres as well. Okay, so this symbol means if and only if, so they are equivalent true-false statements. And so we've got this nice little proposition that says, hey, if I've got the mean value property for balls, then I actually have a mean value property for spheres, and I can represent the mean value property for spheres the exact same way as I did above. The only difference is that, hey, look at that, I've got a partial sitting in there indicating that this is the boundary of the ball, which I integrate over, and then the ds means that I'm just integrating on the boundary rather than integrating on the volume. That's why it was a dv earlier. dv for volume, ds for surface, so it's the surface integral. But the statements are the exact same, where if I take the average over the entire integral, I get the value at the center. And they're equivalent statements. And I have a little proof here. You don't have to read the proof. It's pretty long and really doesn't really explain too much about what's going on. But we care about these objects because they're mathematically useful. you can say, number one, if you've taken complex analysis, every complex analytic function, the real and imaginary parts are harmonic functions, which means that they satisfy the mean value property, it means they satisfy Laplace's equation, et cetera, et cetera. But for other reasons in math, we also care about this because we care about functions which evolve over all of space as the average value over regions of space, right? That seems like a very natural thing to ask if everything is an average of its regional integrals. So we're going to jump back to this PDE of the Laplace's equation, and let's just recall that this delta, you can think about it as nabla dot itself, you can think about it as the sum of all partial derivatives squared. You can think about it however you want to think about it. We're just going to take that, we're going to act it on a scalar field, and we want to get 0 out of it in some domain. This is called Laplace's equation, named after Pierre-Simon Laplace, some French guy from the 1700s probably, maybe early 1800s. And solutions to these equations are called, so the scalar fields which solve them are called harmonic functions. So you'll see a lot of people refer to functions being harmonic in specific domains, and every time you hear that, you want to think about Laplace's equation. But in fact, what you want to think about also with harmonic functions, the reason why people care about them is that harmonic functions, Laplace equation, etc., it's all the mean value property. So these all kind of mean the same thing. It's the mean value property for balls, right, or spheres. If you change the shape of the domain that you're asking for the mean value property over, obviously you're gonna be asking about a different equation, but kind of the generic spherical mean value property is equivalent to a harmonic function, is equivalent to Laplace's equation, satisfying Laplace's equation. So that's what this theorem is. It's kind of the main theorem of this entire section. It's just that the harmonic function or solutions to Laplace equations occur if and only if the mean value property is satisfied. And so this is just more motivation for why we care about solving this particular PDE. I go through a proof. We get into calculating outward unit normals and so on. So the proof is there if you're interested in proofs. If you're not, don't worry about it. And then we're going to look at one example of a solution to Laplace's equation to get an idea of maybe what does a function which satisfies the mean value property look like? What does a harmonic function look like in our intuition? So I'm just going to present you with Laplace's equation as well as a boundary condition of x squared. We're going to be working over the unit square. So our domain omega is the unit square 0, 1, 0, 1. And we have some values, some height. The function has a height over this unit square. So you can imagine there's some height there. Now it's not quite that crazy, but on the 0 edge for y, so that's when y equals 0, that's along this line, we say the height's going to be x squared. So I guess that's just something like this. On the 0 value for x, it's negative y squared. So that's over here. Negative y squared kind of goes downwards like that. On the 1 value for x, it's x squared plus x plus 1, which is probably something like this. Kind of comes up and peaks there. And then on the 1 value for y, which is in the back here, it kind of probably comes, or 1 value for x, it kind of comes down and connects back up. So let's just jump down. I've got it in red here. This is kind of a side angle view. So we're looking, there's the one edge of the square when x equals 0, or sorry, when y equals 0. This is the edge of the square when x equals 1, the edge of the square when x equals 0, and then the edge of the square when y equals 1. So that's what's going on in this picture that I've got. And I just say, I was smart and went ahead and solved this for you. But here's a function which satisfies the entire PDE. Let's go ahead and verify that it is harmonic. So we'll verify that its second derivatives do go to 0. So we take all the second derivatives, we get a 2 from that term, a negative 2 from that term, and we'll get 0. And then if we plot actually the value of the scalar field in gray here, you can see how this kind of interpolates, right? It's gonna interpolate the boundary. So it definitely needs to interpolate the boundary, but in fact it interpolates it in such a way that the mean value property is satisfied. This is kind of the point of Laplace's equation. The mean value property is satisfied. So that means if I took any ball in 2D, which a ball in 2D is just a disk. So if I took a disk and I took the integral of that gray surface over that disk, the average value of the integral has to be the same as the value of the scalar field at the center of the disk. So there's Laplace's equation. We'll jump over to the heat equation. And with respect to the heat equation, I already did cover a very nice derivation of this in example 1.1.22. But we're going to cover a different one because I think there's good perspectives to be had from both. And the perspective we're going to have on developing the heat equation is going to be diffusion. Okay, so rather than heat, we're going to actually allow ourselves any form of diffusion. So this could be a gas, just kind of spreading throughout a room. This could be a drop of food coloring in water. if it's small and if the water's not being stirred or anything, we're just going to let the Brownian motion of the water kind of disperse the food coloring. Any form of diffusion like that is what we're going to think. And we're going to try to develop an equation which properly models diffusion. We'll find out that that equation is the same as the heat equation. So you can think about heat and diffusion kind of as similar processes. But let's actually develop this using some intuition, starting with the idea of Brownian motion. So if you haven't heard of Brownian motion before, this is kind of the motion that dust particles experience, and actually a lot of other particles experience. But if you've ever kind of been able to see a dust particle in the air, it moves fairly erratically, right? It kind of juts around in a lot of really random directions at any point in time. And certainly there are air currents that cause this to happen. But there's other things that are causing it to happen. So actually in the absence of any true air currents, you still get this very erratic motion of the dust particle through air. And it's just because of random collisions with gas molecules. They impart enough energy on the particle to send it in any specific direction every time it runs into the particles. So you get this very erratic motion, and it's basically randomly pushed at any given point in time in a random direction. So we're gonna see if we can model the behavior of the probability. This is what we're gonna look at. At time t greater than 0, what is the probability of finding the particle at place x and rd? And you may be thinking that it's strange that probability is showing up in PDEs, because if you've taken a probability course, you probably didn't see too much PDEs in that course. But really the difference, there's so much PDEs in probability when you get to what's called infinite dimensional state spaces. So when the probability, the total number of events that you're calculating probabilities over is infinite, you actually run into PDEs quite often. And so we're going to develop a PDE that describes the probability of finding the particle at some place, and certainly because there are infinitely many places we could find the particle, that's why we're setting PDEs. So let's think about, we're not going to be mathematically rigorous about this. You probably have to be a graduate student and take a course in stochastic analysis to figure out, make this very rigorous. But in a way that's slightly less than mathematically rigorous, we will be able to develop a PDE that works here. And the way we're going to do it is give ourselves, our solution to the PDE, whatever it's going to be, solution to PDE at time t and place x vector, right, will be the probability density of the particle at the place x and time t. So we're going to start with that being the solution, then we're going to try to derive a PDE that's going to make sense for us. So let's think about it. We're going to use the properties of Brownian motion to calculate how such a probability might evolve over time. So let's start at some time t0 and push ourselves forward a little delta t amount of time. So we're going to arrive at the point t plus delta t x naught and calculate the probability at that point. But to have arrived at that point, the particle must have moved some amount r from a random direction, right? So maybe this is my point, t naught plus delta t is my current time, and then let's say that this is the point x vector 0. To have come here, it must have come from some direction of distance r at time t naught. So it must have been at one of these points at time t naught. But let's be clever. It's random, which means all of the points in the sphere around, the sphere of radius r around x naught is where it must have come from, right? And it could have had an equal chance of coming from anywhere around this sphere of radius r to end up at x naught. And so the probability that it ended up at x naught at this later time has to be the average value around the sphere. And so keep in mind this partial b, as we just saw in the Laplace equation, is the sphere. It's the boundary of the ball. So this partial b is saying we're going to average the value that it used to be at the earlier time around this sphere, and we're going to call that the density at a later time. If we make a change of variables to actually try to calculate out maybe what is this right-hand side actually doing, right? So let's actually try to calculate out what this average value is. We'll make a change of variables from x to the center of the sphere plus its radius times a vector, okay? So what that does is it reduces my sphere now to the unit sphere centered at the origin, which is a lot easier to calculate. And I've pushed kind of all of the behavior of the sphere into, pushed all behavior of the sphere into phi. Once I push all the behavior of the sphere into phi, I want to figure out how phi kind of depends on x. And we can do that using the d-dimensional Taylor series. So this jumps back way back to chapter 2, where I introduced the d-dimensional Taylor series to all of you. You're probably wondering why it's so important to actually compute. Well, what we can do on this phi, if we just forget about time as a variable here, we're just going to do the Taylor series in space. If we calculate the Taylor series in space d-dimensionally, that's the definition that you'd see in chapter 2. But in fact, if we expand this definition, we see, okay, it's equal to phi at the center, and then the first derivative of phi at the center times x times r, and then the second derivative times x squared times r squared over 2, and so on and so on. This big O notation just means that as r goes to 0, the rest of the terms go to 0 like r cubed. Okay, so they're going to be going to 0 on the order of r cubed, which means that as long as r doesn't tend to 0 too quickly, really these first terms are the only ones that are going to matter for us. So if we expand this phi in terms of its Taylor series, so I'm going to replace the entire Taylor series into this integral. I'm going to put this entire term into that integral. What I get is the following integral, which has a term dependent on the center, it has a term dependent on the first derivative, a term dependent on the second derivative. There's the center, the first derivative, second derivative, and then, hey, we're still just going to let that last term tend to 0 fairly quickly, because the idea is if we've waited a delta t amount of time, we're going to actually push delta t down to 0. That's going to give us a time derivative. So we're asking questions about time derivatives here. And then the radius will tend to 0 in the same way. So let's forget about higher order terms on the radius and just consider the first 3. Well, if we look at this, that's the average value of a constant. Since you know I'm integrating over x, but that's an x naught, so those are different variables. So this is the average value of a constant. This must just be phi at t0, x0. This is now the average value of, there's a constant, right? That's a constant. This is x. That's the average value of x over average value of x over unit sphere. Well, what do we know about this? Let's test the second derivative of the variable x. It's got to be 0. That means it's harmonic. That means it's the average value is the value at the center of the unit sphere. The value at the center of the unit sphere is 0. Okay, so in fact, this entire term becomes 0 when we integrate it. And so I've got this one, which is phi of t naught x naught. I've got this one, which is 0. And then I've got this last term here. And we're going to let that r cubed term sit around for a while. And then I have the last term here. And I'm going to ask questions about the last term in a bit. So if I scroll down, you can see I've replaced my first term with just the value. The second term I replaced with 0, which is why it's missing. And the third term, I've simplified a little bit. I pulled my Laplacian out. Notice that what I have up above here is bigger than the Laplacian. That's the Hessian. But if you get clever about how the Hessian integrates over the unit sphere, in fact, because the Hessian contains all sorts of these mixed terms, all of the mixed terms end up integrating out to 0. That's for the same reason as we saw before, where this, the Laplacian of all those terms would be 0, right? The Laplacian of xi, xj will definitely be 0. So all of the mixed order terms over the unit sphere will be 0, and I'm only going to pick up the second derivative terms in the same variables, which is going to be the Laplacian. So I replace the Hessian with the Laplacian. The price I pay is that my outer product on this x variable becomes the magnitude of the x variable squared. Okay, so I'm going to integrate the magnitude of the x variable squared over the ball. That ends up turning out to actually be the same as the ball itself. This is because we're asking questions about, hey, the magnitude of x squared is just the magnitude of the vector x on the unit sphere. Well, the unit sphere is the sphere where everything has magnitude 1. So in fact, that's just magnitude 1. This entire term is just then the total area of the unit sphere. And the total area is going to cancel with that total area. So we actually have a lot of cancellation that happens. We find out that when I moved a little bit forward in time at some spot, that's actually equal to me coming from somewhere else earlier. It's the original value at the center. And then where did I come from? It's r squared over 2 and then the Laplacian on phi. And then I've got these lower order terms in r cubed that aren't going to show up. Reason being, if I rearrange this, I'm going to bring these two terms together and I'm going to divide by the r squared. I'm going to divide by r squared and bring those two together. This looks very much like a difference quotient. Okay, so it's approximating it's approximating the time derivative so long as r squared equals delta t, right? Or as long as r squared is proportional to delta t. I'm actually approximating the time derivative. And we can think about, yeah, r squared should probably approximate be on the order of delta t, because you'll recall that delta t was the amount of time I waited for a particle to need to come from the sphere into the center of the sphere. And when I divided by r squared, my order on r cubed turned into an order on r, but of course as r tends to 0, this is still going to go to 0. So what we get is as r tends to 0, that's going to be like partial t of phi, and we've got our Laplacian on the right-hand side. What is this going to end up looking like? It's partial t of phi on the left-hand side, some diffusion coefficient alpha times the Laplacian on the right-hand side. So this really is our heat equation that we already saw. Partial t of phi is delta phi. That's going to be both diffusion and heat. So there I've got the definition of the heat equation. The PDE partial t of phi is alpha Laplacian of phi. And you'll notice that I've dropped the dependence on x there. You should be clever enough every time you see the heat equation to know that that delta is only referring to derivatives in the spatial directions. But a lot of times it's stated without putting a sub x next to the Laplacian. So let's look at one example here. This is just an example to get an idea of how these things behave. Suppose I start out with my lovely heat equation when alpha is 1, and I give myself some initial density, right? This is the initial Gaussian density over two-dimensional space. So I've got a nice Gaussian density, and I'm going to let that evolve over time. We can find out that the following solves this heat equation by first plugging t equals 0 in. And what do you know? It actually equals the Gaussian density. And then if we take a time derivative and compare it to a space derivative, they are exactly the same. Or two space derivatives, right? If we do the Laplacian, we get exactly the same thing. So that's how we can verify something satisfies a heat equation. If I show a picture of how this evolves over time, it does kind of what you'd expect it to do. We've got a little bit of a sharp peak right away. It's not super sharp, but definitely it kind of diffuses out over time, right? It's getting weaker and weaker, the peak, kind of just spreading out into everything. And like I said, with the diffusion, we can think about any point here, like, okay, let's assume that the particle was originally distributed fairly locally. If we wait long enough, then the particle is going to be distributed very broadly with diffusion happening. If I made this even more of a peak, it would still spread over time. So even if we knew with very high probability where a particle started out, if it's subject to diffusion, it's going to spread over time. Finally, we'll jump over to the wave equation, which is one that we did introduce in chapter 1, but we didn't actually go through much of a derivation for how you could come up with it. And this one's pretty easy to derive with our information from chapter 1, because what we're going to do with a wave equation is we're going to think about a membrane which is stretched and released. Because why is a wave actually a membrane that's stretched and released? Think about the surface tension. The surface tension of water actually does behave quite similarly to a membrane. And if you disrupt the water in any way, you've basically stretched it in one direction, then you release it once the force stops. And so we're looking at kind of how does a membrane evolve over time if you stretch it and let it go. So we're going to give ourselves a scalar field, which represents the height of a membrane away from equilibrium. And what do we know? We know that if we're going to predict the motion, we know that we can predict its acceleration by thinking about the sum of forces on the membrane. Thanks to Newton, F equals ma, right? So acceleration equals force up to a mass constant. So we're just going to try to derive all of the sums of forces on the membrane at a point. And if we jump back to example 1.1.21, trying to determine the forces on a membrane at any point, we actually found out, this was for the soap film, it turns out that the forces on a soap film are equal to the surface tension. So you can imagine if I've got a membrane and I kind of disrupt it away from equilibrium, the local force on my membrane, maybe right there, is totally equal to the surface tension on that point. There's tension pulling it back towards equilibrium, and surface tension is proportional to curvature. So, you know, the higher curvature you have on a membrane, if you really stretch it out really far, really kind of spiky, that's going to have a really, really high surface tension because its curvature is very high. And you can calculate the curvature just from, this is just directly out of calculus 3. You just define curvature kind of as it's the radius of the sphere, which aligns with the area locally, tangent. Maybe like the radius squared or something, but it's related to the sphere that aligns tangent to the surface there. You can just calculate that with calculus 3 as the following. And we get that the membrane has to evolve according to this equation. Now, that is not the wave equation because of what's going on in the denominator here. It's nonlinear because of what's going on in the denominator. Nobody likes working with nonlinear equations. They're often too hard. And so we make this lovely physical assumption of assuming that the denominator is approximated by 1. We assume this is close to 0. So by assuming that that's close to 0, we say the denominator is approximately 1, and we actually derive our wave equation getting a dot product of gradients with themselves, which once again is the Laplacian. So this Laplacian shows up in all of our Holy Trinities. And then the difference between the rest of the Holy Trinities is that we have 0 derivatives in time, 1 derivative in time, or 2 derivatives in time on the other side of the equation. And so that's going to be the wave equation that I draw over here. 2 derivatives in time is alpha, the wave speed, times the Laplacian in space on phi. We can look at one example of the wave equation here. Here I've given myself an initial condition which happens to be waves as well. No surprise there, these are the initial conditions that work pretty well for wave equation problems if you start with a wave. And let's just see that cosine t plus x plus sine t plus y is a solution to this wave equation by calculating 2 derivatives in time. We get negative cosine and negative sine, 2 derivatives in space. What do you know? You get the same thing. And then if we evaluate this at 0, 0, 0, we definitely satisfy the initial condition. So this works on the wave equation. And if I display some nice images of how that evolves over time, you can see it doesn't really look like it's moving because these images are just kind of hard to decide. But if you look really, really carefully, let's grab that point there, then it moves here, and then it moves there, and then it moves here. So this point is actually moving in this direction. It's kind of hard to see because there it's at the end. There it's kind of been covered up, and now it's gone. You have to start at a new one, and it's moving in that direction. So these waves are in fact moving. It's just not very easy to see that they're moving. And they propagate over space. They don't gain or lose energy. That's kind of a very common thing about the wave equation. So that's all I've got. It's called the Holy Trinity. And then we'll basically spend the rest of this chapter trying to classify and solve this Holy Trinity. It's basically the sort of equations that anybody will ask you about if you leave this course and tell them that you passed PDEs. They're going to be like, oh, tell me about the wave equation, tell me about Laplace's equation, and so on. These are really the classics. So keep them in mind, keep their physical representations in mind, and I'll see you in the next class. Bye.